Alright guys, just at the end of the last part of the video we had found the direction numbers for the two lines, line 1 that was given and line 2 that we created, that lie inside the plane. And we're about to take a cross product to find the normal vector that would help us define that plane that we're interested in. So we went into the matrix editor in the TI-89 and we entered the matrix ijk. And then we have the values -2, 5, and 4, which came from the direction numbers of our first line. So -2, 5, and 4. And then the line we had just created was -2, 3, and 9, so we entered that second. And then when we go home and take the determinant of that matrix, we'll get 33 I hat, 10 j hat, 33 I hat, 10 j hat, and 4 k hat. So those are going to be the direction numbers of the normal line that defines our plane. And then we can plug in any one of the points and that normal line in order to define the plane. So I've picked the point 0 or 6, 0, -2, so you can see x minus 6, y minus 0, z minus -2, so z plus 2. And you can see our direction numbers show up in the coefficients. They're 33, 10, and 4. We set that equal to 0. That would be a perfectly acceptable answer. We could also collect our terms and get the linear equation, and that would be equal to 190. So either of those is correct. All right, let's do one last question. Let's find the distance between two parallel planes. So we'll actually do the problem on the next page. Let's see, or actually, let's do, we did the example here. So we'll go back to example 9. There aren't very many of these in the homework section. So we're given two planes, and we want to find the distance between them. Now, the only way that question would be reasonable is if the planes are parallel. So we need to check to make sure the planes are parallel first. So the two planes given are 10x plus 2y minus 2z equals 5, and 5x plus y minus z equals 1. So the direction numbers for the first plane are 10, 2, and -2. And the direction numbers for the second plane are 5, 1, and -5. As long as these vectors are scalars of each other, or scaled versions of each other, their unit vector that points along the same direction as them will be the same. And we can see that, yes, the first normal vector that we got off the first plane is actually just scaled by 2. So these two normal vectors point in the same direction, which means that the planes are parallel to each other. So as long as the planes are parallel to each other, we can find the distance between them by selecting any point on either of the planes. So I selected a point on the first plane by looking at the place where z and y are 0. And so when I plugged in z and y equals 0 into the first equation, I was able to solve for x and get 1/2. So there's a point on the first plane that's 1/2, 0, 0. Or another way to say that is that the plane passes through the point, the first plane passes through the point 1/2, 0, 0. Now that I have that, I can use the direction numbers from the second plane in the distance formula that we defined in class. And so in this case, I've put the direction numbers 5, 1, -1 from the second plane. And the point 1/2, 0, 0 here, the value of d is -1, so I put -1 over here. And then here again is the magnitude of that normal vector. We divide by that, and we get that the distance is √3/6. All right, so there's an example of most of the things that we've covered in that chapter. if you have other questions or you want to see more examples, go ahead and email me and I will respond with appropriate material.